Starting again on a thick-walled pressure vessel. Technical difficulties at the end of the last one, notwithstanding. So this is the only case in this course where we will consider a true three-dimensional stress state. When these pressure vessel walls become thick with respect to the diameter of the vessel, then our thin-walled equations no longer work. And one common place that you'll see a structure like this is a hydraulic cylinder, very much like the bookshelf with too many books on it. The stresses in the structure like this may be well below the yield and may have a very high factor of safety, but the deflection is unacceptable. We've got a saggy bookshelf. In the same way, the deflection of the walls of a hydraulic cylinder have to be very minimal so that the hydraulic fluid doesn't leak out. So this is a three-dimensional stress state, as I said, and we have, instead of a sigma x, sigma y, and sigma z, we have a stress in the radial direction, we have a stress in the hoop direction, and we have a stress in the axial direction. The new one is this radial direction. We've dealt with hoop and axial with our pressure vessel problem that we've done already, and the fact that it varies within the thickness is this new radial stress. So the example that we're going to look at is this hydraulic cylinder. It's got a 2-inch inner diameter and a 1/2 inch wall thickness. So across here is 2 inches. We know that the inner radius, r sub I, is 1 inch, and the wall thickness is 1/2 inch. So we have r sub out is 1.5 inches. And back over here are our governing equations, where all three of them have this same initial term. We have this inner radius times the pressure over the difference between the inner radius and the outer radius squared. So in this case, this would be 1 inch squared times 5,000 psi over 1.5 squared minus 1 squared. Or that simplifies to 5,000 over 1.5 squared. That's the same coefficient term, and it is in fact the axial stress, which, as you'll see from the plot over here on this side, is a constant value. So this is our 1 squared times 5,000 over 1.5 squared minus 1 squared is, in fact, 4,000 psi. From that expression, there is no radial coordinate in the expression, so it is independent. And I'll come back over here, that this axial is independent of radial location. There is no r in the expression. Now, looking at what happens with the other two expressions, looking first at the radial, we have this same coefficient that is 4,000, and then we have this other term that is 1 minus the outer radius over the radial location squared. The outer radius squared being the numerator. As I vary, come back over to my plot, as I vary from the inner radius to the outer radius, the ratio of the term in the expression goes to 1. So at the outer radius, so R0 over R0, this tends to 1, and so therefore this second term tends to 0. And if we look at our plot, that is in fact what we see, that we go from a value tending upward and ending up at 0. If we look at the expression for the hoop stress, on the other hand, which has jumped, if we look instead at our expression for our hoop stress, we have our same coefficient, which is 4,000, and we have a term that is 1 plus this ratio of the outer radius over our radial location. Well, as our radial location goes from the inside, which is 1, it's a smaller number than the outer, and it converges to the outer radius, so this term, where in the radial case the term tends to go to 0, in this case this term ends up tending to the value of 2. And as we go from the inner radius to the outer radius, in fact we see that we go from a larger number tending down, so that that multiplier factor ends up at 2, and we are in fact at 2 times the axial stress. And summarizing some of these observations, is that our radial stress sigma sub r is equal to minus p at the inner surface, and it increases to 0 at the outer surface. And that stands to reason if you think about what's going on. It has to be in equilibrium with its immediate surrounding. So it is subjected to the pressure inside the vessel at the inner surface, and it has to be in equilibrium with no net pressure on the outer surface. Our hoop stress in the theta direction is the greatest at the inner surface. And it decreases by an amount P from the inner to outer surface. And last, as we pointed out first, our axial stress is constant. If we want to compare, or rather if we want to look at where our worst case scenario is, it is at the inner surface. And those values, those critical stress values for our stresses in the three different directions, when R equals R sub I, again in our radial direction, that simplifies out to a value of minus P. In our hoop direction, we have the sum of the squares of the radii times the pressure over the difference of the squares, and in the axial direction, we simply have the inner radius squared times the pressure over the difference. If we have a new variable that we call capital K, that is the ratio of the outer to the inner radius, or an indicator of the thickness, we can compare the maximum hoop stress from the thick-walled equations to our assumption from the thin wall. So we can solve our new variable. We can say that R sub 0 is K times the inner radius. So if we use our thin-walled equations, we have stress in the theta direction is P times the radius over the thickness. The thickness is the outer minus the inner. We said that the outer is K times the inner. So I can say that the thickness is K minus 1 times the inner radius. Okay, taking that back into our expression for the hoop stress, we have the pressure times the inner radius over K minus 1 times the inner radius. Inner radius cancels, and we have that the hoop stress is the pressure over our factor minus 1. The thick-walled expression, the maximum happens at the inner wall, so our sigma theta submaximum is our outer radius squared plus our inner radius times the pressure over the difference of the squares. So this is substituting in our definition of R sub 0, pressure over K R sub I squared minus R sub I squared, and with the same simplification, we have a actually, by simplifying out the r squared, we have k plus 1 times the pressure in the numerator, k minus 1 in the denominator. Okay? If we now look at how these vary, alright, after yet one more Microsoft Word crash, we have cast our thin-walled and thick-walled equations in terms of our new variable k, which is the ratio of the outer radius to the inner radius. And we're looking at the difference in our hoop direction at what different ratios make in the thin wall or thick wall equations. So for different ratios, we have hoop stress from the thin wall equations, hoop stress from the thick walled equations, and a percent difference. So when and k is the outer radius over the inner radius. So when you do have, in fact, a very thin-walled structure, and your ratio, the outer radius to the inner ratio is 1.01. You plug that in to our thin-walled equation, and you get 100 times the pressure is the maximum hoop stress using the thin-walled equations, and using the thick-walled equations you get 100.5025 times the pressure. That is, in fact, 0.5% difference between the two. If we then have a 1.05 K, that maximum pressure is 20 using the thin-walled equation, or 20.5122 times the pressure for the thick wall. Then you have 2.5% difference. At 1.10, the max is 10 times the pressure with the thin-walled approximation, or 10.523 for the more accurate thick wall. That is getting close to a 5% difference. For 1.2, we have 5 times the pressure, or 5.54, which is getting on towards 10% error. And for the example that we just did, where your outer radius is 1.5 times your inner radius, that maximum pressure is 2 times the pressure using the thin-walled assumption, and 2.6 times the pressure with the thick wall, a 23% difference. So, to sum up, if k is less than 1.10, or if the thickness of your wall is less than about 1/10 of the radius of your pressure vessel, the error when using the thin-walled assumption is less than about 5% when using the thin wall equations. So that's another one of those engineering rules of thumb.